Hello and welcome to our talk. We'd like to thank StreamNative for organizing the Data Streaming Summit this year and letting my coworker and colleague Bonnie and I speak about Flink SQL changelogs and why you should care about them. So Bonnie and I are staff software engineers at Confluent, and we work on the same team where we dive into the details of Flink SQL and understand things there. So, um, yeah. So first, let's talk about a little bit about what Flink SQL is. So Apache Flink is a distributed engine for bounded and unbounded computation, and the SQL level is the highest level of abstraction. It's built on top of the table API, and these are built on top of lower level APIs that are more flexible but a little bit harder to use, like the data stream API and the process functions layer, where you can get down in the weeds and write your own timers and watermark strategies. So the SQL level and also the table API, they use Apache Calcite to handle planning and optimization um, parts of the lifecycle. So a SQL query is first parsed into a logical plan, and then Calcite optimizer rules and additional optimizer rules from Flink itself help us turn that logical plan into a physical plan. So we'll look at a motivating example here. On the left, we have an input table, products, and we've named a few of the columns that we'll be using in our query. And in the lower left, we have our, definition of our output topic. And what we're going to do on the query on the right is over time for each category, we want to calculate a cumulative revenue that we've, earned with that category. So if everything was run in batch mode, we'd see some pretty familiar operators. We're going to talk about streaming SQL today. So if we look at the physical plan, since we've simplified the query quite a bit, we can see where we're reading from a table, going through some nodes that we are pretty familiar with. We're not surprised to see something that says exchange or calc for doing some operations. And the over window, having an over aggregate operator makes sense as well. Changelog normalize is interesting, and Bonnie will be sharing more about that later. If we dug into some of the physical details of the plan, there are things that we'd see like primary keys, which we're pretty familiar with, but then there are going to be other details like this changelog mode that that's what this talks about. So first question is, what do we mean by a changelog? And a changelog is a record of all the changes that have been made to a database table. So this could be the bin log in MySQL, and we'll talk more about what it looks like in Flink. Other databases have similar notions. And at this point, I'll hand it over to Bonnie.
Thanks, Jim. So let's talk about changelog modes in Flink. Flink uses four types of changelog modes: insert, update before, update after, and delete. By default, whenever you create a table, the default mode is insert. You can also specify retract or upsert mode if you're dealing with updates. Each one has a notation like plus I for insert, minus U for update before, plus U for update after, and minus T for deletes. Uh, in general, like to summarize, you can think of you could have append or insert only streams which emit plus I as the changelog mode. Updating streams can be classified into retract and upsert. Retract is also known as the full changelog mode or proper changelog mode, which can emit plus I, that is insert, update before, update after, and delete. Whereas upsert, it definitely requires a primary key to be specified, and it can emit plus I, that is inserts, update after, and deletes. Using upserts can also save some bit of network traffic since it swallows a lot of update befores. Here is an example of how changelog flows through the pipeline or the plan. Um, you can see that on the top that there's inserts if your source consumes or produce, like if you're consuming only inserts from for example like a Kafka append only log, inserts flow through the system, but depending on some of the operators that you use, like for example if you're using a group by or over aggregate with non-time attributes, you may end up consuming inserts but producing more than an insert. Like you may end up producing update befores, update afters. In general, like you may start in the append mode and live in the append mode forever for simple queries. Example, reading from a Kafka append log and writing to a Kafka append log, maybe a simple select star query. But if you use more complex queries, as you can see you in the diagram above, you may start in append mode, but you may transition to the update mode. And once you transition to the update mode, you tend to live in the update mode, either retract or upsert. Sorry, retract or upsert. Yeah. Until Flink 2.1, it was not possible to transition from once you go to update mode, it was not possible to transition back to insert mode. But Flip 440 introduces process table functions that allows you to do that. And the rules for you are present in the planner, where you define for each operator what it can consume and what it can produce. Like for example, over aggregate with non-time attribute, it can consume inserts or updates, and it can produce updates. Let's see what happens if an operator produces updates, but a downstream operator can only handle inserts. For example, if you use an over aggregate with time attribute, it can only consume inserts and produce inserts. So if you have a group by before an over aggregate, the group by can produce, technically it can produce inserts and update befores. But if that comes to the over aggregate cannot, with time attribute, cannot handle that. In such cases, Flink throws an exception, something like it tries to give a clear exception that over aggregate doesn't consume updates, which is produced by a node before that, in this case, group by. Let's see what happens if Flink SQL operators ignored certain changelog modes. Let's take an example of a simple group by. We have a table here with users, which has user ID, department, and a boolean to indicate whether the user is active. Let's insert two rows. Alice belongs to HR department. Bob belongs to IT department. They both are active users. And let's start a continuous query with group by, assuming that group by only consumes inserts and produces only inserts. So if you do a group by and see users belonging to each department, you may see that HR is one and IT is one, and both have a changelog mode of +I. And that is absolutely right. But let's say if Alice decides to switch departments, in this case, it will correctly emit that IT has two users, but the previously emitted value of HR as one is now invalid. To fix this, group by should ideally emit an update before for HR with the previous value and an update after for HR with zero. That's when the previously emitted value gets corrected. So here we can see why we need to handle update befores, update afters in certain cases. So operators have different implementations based on the changelog mode. More complex operators can lead to large state size. It can also produce a lot of network traffic, lead to increased latency and compute. Let's take a quick look at an example of over aggregate with time attribute. Here we have a sensor reading table which is calculating an average temperature over a 5-minute window. The over aggregate is partitioned by sensor ID. The data within that partition is sorted or ordered by reading time, and you're only looking at 5-minute windows. So the state size that the operator needs to keep is limited to the number of records within the 5-minute interval, which may not be very huge depending on the amount of traffic that you receive. And since the over aggregate with time attributes can only consume inserts and produce inserts, for every insert, you may see an insert coming out. Network traffic is also 1:1 there. Computation is done over 5-minute window, so your latency depends on that as well. Um, let's compare that with over aggregate for non-time attributes, which was introduced as part of Link 19 of 59. Um, uh, s- uh, yeah, somewhat similar query. Um, but here we have a products table, which has the year month data, has product ID, it has a category. And let's say we want to calculate the cumulative revenue for those for by category. So you have this, you partition the data by category, you order by year month. So you want to receive updates as data comes through. And the only thing it supports is range between unbounded preceding and current row. So if you look at the plan, you have a source, you scan the data from the source, you have a calc exchange and then an over aggregate. And this over aggregate is a non-time over aggregate, which means it can consume inserts, but can produce produce retracts. And we'll see with an example why. So you have this initial state P0 let's say a product ID with P01 belonging to a category electronics comes in. You compute the cumulative revenue, and for that it maintains data in sorted state by year month, which is a string field, and it emits the result of the cumulated revenue. Let's say next record comes in, it inserts it in the sorted table and produces an insert for the cumulative revenue for that month. So right now, the previously emitted value is correct, and also the current emitted value has the right cumulative value. Similarly, for product ID P05, which comes for the month of May, and another product with for June. In that case, as you can see, for every insert, we emitted an insert only output with the right cumulative value. But let's see what happens if an out of order insert comes in. Like we get an out of order data for the month of April. What we do is we compute the cumulative value for that. But now all the previously emitted values for the month of May and June are incorrect. So what we need to do is we emit the value, cumulative value for the month of April, but we go back and retract the values and update the state as well. And when we update the state, we also emit out the previous value in the form of minus u and the current value in the form of plus u. So you can see the results here. Uh, and if your source can support retract, initially we discussed our source could only support inserts, but in case your source also supports retract, you could get a minus u, in which case you would find the element in the state, you remove the element from the state, and thereafter all subsequent elements after that also gets affected. So you emit a minus d for the element that was deleted, and a minus u and a plus u for all the values affected after that. Some of the performance implications of using over aggregate with non-time attribute, your state size can grow because it needs to maintain the entire state for every key. A data skew can be a problem. So make sure your data is distributed, or when you partition by, you partition appropriately. Serialization and deserialization costs can increase for complex records, because for every record that comes into the over aggregate, we have to read data from the state and write it back to state. Network traffic can also blow up, because for each input, as we've seen, you could potentially emit multiple records. Now, if your sync supports upsert semantics, and let's say the upstream is producing full changelog mode, the optimizer may decide to add an upsert materialized to the sync. In that case, you can see that in the compile plan or in the explain next to the sync, you may see something like an upsert materialize is true. Um, let's look at how the sync upsert materializer emission rules are followed. When the planner adds a sync upsert materializer, it distinguishes between inserts and deletes. And for insertions, um, for the first record, it emits an insert. All subsequent records matching the same upsert key are emitted as update after. For deletions, if the state becomes empty, a delete is emitted. If otherwise, and for an update before or a delete, um, it will update the state, but it may emit an update after for the most recent element. Deletions of already updated elements are swallowed and not emitted. This reduces number of events emitted to downstream, but can add a lot of state. Let's take a look at this with an example. Now, let's assume that the upsert key is the same for all the records for this example, and let's see how the state grows. So the first record comes in with an insert. Since the state is empty, we add that to the state, and the result is emitted as an insert since it's the first element. When the second element comes in, it's added to the state, which becomes the most recent value for that upsert key. And since it's not the first element in the state, an update after is emitted. And if there's an update for an existing value in the state, the sync upsert materializer finds that element in the state, updates it, and sends an update after for that state, for that key. Now, if an update before comes in for an element in the state, it finds it, removes that from the state. But since it removed the last value from the state, the most recent element from the state is emitted out, which in this case is Alice updated, and that a plus U is sent for that. If a new record comes in through an update after, that's added to the state, and an update after is also emitted correspondingly. Now, if a minus D comes in for Robert, the sync upsert materializer finds it, removes it from the state, and since this is similar to the case that we saw before with the minus U, since it's the last element that's removed from the state, the most recent element is emitted as an update after. Now, when a minus D comes in, which is the last element in the state, it's correctly removed from the state, and a minus D is emitted in this case. As you could see, the state can grow a lot if the upsert key is not unique. So it's, if possible, if you can define the good recommendation is to have the primary key for the source and sink match whenever possible. And if you're using if you're partitioning the key through group aggregation or over aggregate or join, if the partition key can be defined as the same as the primary key in the sink, that will help not have an upsert key. And the sync materialization can be avoided in certain cases there. Now let's look at a case where if your source supports upsert, and you do that by defining a primary key, you know something about the table that you're reading from, but your sync supports full changelog mode. That means you're expecting that you get the full changelog mode. In that case, the planner, what it does is after the source table scan, it adds a changelog normalized node, and this changelog normalized node has a special meaning. It basically is responsible to convert an irregular stream like an upsert stream into a full or a proper changelog stream. It can do duplicate detection, and the primary key, and it uses the primary key for that purpose. Let's take a quick example. Let's say you're reading data from a Kafka compacted topic. Let's say it's an upsert stream in that case. So you see the first, let's say you see an insert. In that case, the state changelog normalized node also maintains state. So what it does is it'll add that key to the state and it'll emit a plus I for that. Then when you see a new element with key 102, it adds to the state and it emits the result for that as well. Now let's say an update comes in for the key which is previously present. In that case, it updates the state and it sends out an update before with the old value of that key and the new value. And since it's an upsert stream from Kafka, you may get a partial delete in this form, where the key is present but the value is null. In that case, changelog normalized deletes that value from the state but emits the delete with the full value so that downstream systems can correct themselves accordingly. So I want to highlight Flip 540, which is improving adding some improvements to changelog normalized node when it's not required. For example, if you're reading from an upsert table and writing to an upsert table, potentially there's no need for adding a changelog normalized node, thus saving some state. Also, if you're joining on two upsert tables and if you're using the same primary key for the source and the sink, then it's possible to eliminate the changelog normalized node and thus saving state size. So in general, we've seen changelog mode affects state size, compute, latency, traffic. Some suggestions would be you could define TTLs for each operators if you know your data retention pattern. You could use explain to see how queries are planned. Evaluate what changelog mode. Explain gives you information about what changelog modes are present at each at each node level. The state you can evaluate the state size that explain tells. You could possibly rewrite queries before actually running them. Questions? And thank you.
Awesome. Thank you so much, Bonnie and Jim. That was a great session, great content there. Lovely. I'm gonna check if there are any questions in Q&A. I think this will be the right time to bring it on. You can pop it into Q&A dialogue. Let's just see. Yeah, I think while people are like thinking about questions, I think this recording, as mentioned before in the emails, will be available to you all after the event, so you can go through that. There were a lot of details. I learned a lot in this session today.
Yeah, thanks for moderating.
Absolutely, Jim. Let's see. No questions yet. I think we do have a few minutes. While any questions come up, anything you can add as an extra commentary, Jim or Tony, as we get closer to the end of the session.
Yeah, I think there's a lot of improvements happening in Apache Flink through Flips. I encourage users or people who are interested in that to follow Flips actively.
Yeah. One of the things that I'd like to share is that as I've seen other systems and other thoughts about how to do incremental and streaming SQL, uh, there are multiple ways to represent changelog. So we've talked about how you can do it here in Flink, and I don't think it's intuitive. I don't think it's obvious stuff. So that's why Bonnie and I wanted to talk about it some. Um, yep.
Perfect. Okay, I don't see any questions. I know the next session will start in 5 minutes. Will you be publishing this info on a blog? There's one question. Um, is there any of Bonnie or Jim? David has got a question. Will you be publishing this info in a blog? Um,
Yeah, no plans as such, but yeah, I think document like I feel that each operator in Flink in itself is worthy of a blog and how it works internally. So yeah, I think it'll be the fact that you've asked is quite encouraging, and yeah, we'll definitely look into it. No timelines as such, but yeah, we'll try.
Absolutely. There's one more, I guess, from Suhas. Are there any failure patterns or pitfalls you've seen from customers? I guess regarding the change logs or
Yeah. Just to go back to David's question about a blog post, one of our colleagues, Robin Moffat, recently did publish on his blog about changelog modes and joins. So it's hitting on slightly different things, but I think he just wrote about that. So uh, Robin's just plugging Robin's blog as he continues to write good things there. To Suhas's question, um, I one of the things that we've seen customers run into is some of the confusing errors where you write the SQL query you want and you get an error that says, hey, one of these operators doesn't support the changelog mode that you're looking to use. And if you don't have this information, you'd have no idea what that's about. Bonnie's work here is lifting some of those restrictions. So this is one of the ways that um, we're working to add in more capabilities for Flink to handle a wider range of SQL queries.
Yeah, just to add to that quickly, the customers usually also report a lot about state size, and they don't know why state size grows. It's because Flink adds these intermediate operators like changelog normalize or sync upsert materializer, which maintains a lot of state. So yeah, which can definitely lead to cost. So having just knowing about what Flink does or the planner does internally kind of helps you understand why that state size grows. Additionally, you can also plan your queries accordingly with explain to see if you can avoid that in certain scenarios.
Awesome. Great. I don't see any other questions. We'll give just another 10 seconds or so, just to give you 5 minutes to get ready for the next session, like mainly for the attendees. All right. I don't see any other questions right now. So I think again, Jim and Bonnie, thank you so much for the awesome content. I know this will be available as a recording, and then you've already pointed to some of the blogs where there's a link there. So thank you. I see Bonnie is posted there. So thanks for that. If there are no other further questions, then we can end the session today. And again, have a nice day. Rest of you, of course, continue to join the other sessions. But again, thanks, Jim and Bonnie, for this awesome content.
Thanks,
Yeah,
Kunal, for hosting.
indeed. Thank you.
Thank you. Bye-bye.